Okay, this is the third video for Section 1, Chapter 2 in your Pearson Trigonometry textbooks. This particular video is going to review the idea of the special right triangles, which you should remember from Geometry or Algebra 2. They are the 30-60-90 right triangle and the 45-45-90 right triangle. Now, the reason why these triangles are more important than other triangles is we see them a lot more often. And the main reason that we see them a lot more often is their relationship to the regular polygons. A regular triangle and a regular quadrilateral, a square. So here's the deal. Here's where these triangles come from. Here's why they are important. If we drop the altitude of an equilateral triangle straight down, what that does is it breaks that equilateral triangle into two right triangles. And from geometry, we should know that in an equilateral triangle, that this altitude actually is all of our major types of segments in a triangle. It's the altitude, it's the median, it's the angle bisector, and it is the perpendicular bisector. It's all the same thing. So what we've done is we have broken that 60-degree angle into two 30-degree angles, and we have broken this 2 into two pieces that are 1 unit long each. In other words, if we only look at half of this new broken up triangle, if we only look at 1/2 of it, that is a right triangle that we have called the 30-60-90 triangle. And the reason it is called the 30-60-90 triangle is because those are the angle measures in the triangle: 30 degrees, 60 degrees, and 90 degrees. Now, the original equilateral triangle had side lengths of 2 units, and our 30-60-90 triangle will now have 2 side lengths that we know right off the bat: a hypotenuse of 2, which was the original side, and this base is now 1 unit because it's half of the original 2. If we use Pythagorean theorem, we can establish that the length of the third side is the square root of 3. If you want to know how I did that, let's call it h. H squared plus 1 squared is 2 squared, so h squared plus 1 is 4. Subtract 1 from each side and take the square root. I'm not using a plus or minus symbol only because this is an actual length, and in an actual picture with actual length, length cannot be negative. So our 30-60-90 triangle looks like that. Similarly, if we draw in the diagonal of our square, which has side lengths of 1 unit, that breaks this triangle, or this square, up into 2 right triangles. Now, the diagonals of a square, by definition, which again we should have learned in geometry class, will break those angles exactly in half. It's one of the properties of a square. It's actually, I believe, the property of a rhombus, but all squares are rhombi, so that would affect squares as well. Now notice that in this case, if we look at only half of the square, we are now looking at a right triangle. So that is the right triangle that we are dealing with here. It has legs of length 1. It has 2 45-degree angles within it. And the hypotenuse is the square root of 2. Now again, if you want to see how I did that, if this is x, the length of the diagonal is x, we have 1 squared plus 1 squared equals x squared, Pythagorean theorem, which would be 1 plus 1, or 2, and then we would take the square root to get x. This is our special right triangle, the 45, 45, 90 right triangle. And again, using what we know about similar triangles from chapter 1, we can use that triangle to solve a lot of semi-real world problems. So, first of all, what we're going to do, 30, 45, and 60 degree angles occur a lot more often in trigonometry than anyone is even willing to admit. As a result, 30 degrees, 45 degrees, and 60 degrees, those angle measures, have added value to us in solving real-world problems. As a result, those angles are considered to be more important, and many people, many geometry and trigonometry teachers require their students to memorize the values of those two special right triangles so that they can combine those with SOHCAHTOA to quickly come up with the sine, cosine, or tangent of a 30, 45, or 60 degree angle. So what we're going to do is we're going to run SOHCAHTOA on our special right triangles, starting with the 45 degree angles in our 45, 45, 90 triangle, and we're going to use those values to create a reference item, which we will then use for the rest of this course. So, our 45, 45, 90 triangle has legs of 1, hypotenuse of the square root of 2. So all I've done is I've copied the 45, 45, 90 triangle from the other page. Oops. 45, 45, 90 triangle. Okay? What we are going to do is we are going to use what we know about trig functions to run SOHCAHTOA on this 45 degree angle. So 1 is going to be our opposite, 1 will also be our adjacent, and our hypotenuse will be the square root of 2. So we'll start with the sine of 45 degrees, which by definition, using SOHCAHTOA, will be opposite over hypotenuse, so, which would be 1 over the square root of 2. Now, we should also remember from chapter 1 that that is not in proper notation, so we do have to rationalize the denominator by multiplying the bottom and the top by 2, which would give us a sine of 45 degrees as being the square root of 2 over 2. We can do the exact same thing for the cosine of 45 degrees, the one major difference being that it is adjacent over hypotenuse, ka, SOHCAHTOA, ka, is adjacent over hypotenuse. That would also be 1 over the square root of 2. So just like we did for sine, we have to rationalize the denominator, and that would give us that the cosine value is also the square root of 2 over 2. Finally, for the tangent of 45 degrees, that would be opposite over adjacent, TOA, which would be 1 over 1, or 1. So using SOHCAHTOA, we should be able to quickly come up with sine, cosine, and tangent of 45 degrees. Now, the other three trig functions, cosecant, secant, and cotangent, shouldn't take us very much longer. Remember that we have our reciprocal identities. The cosecant is 1 over the sine. The secant is 1 over the cosine. And the cotangent is 1 over the tangent. They are reciprocals, right? Which means that the cosecant of 45 degrees is the reciprocal of the sine. So if we take 1 over the square root of 2 and we take the reciprocal, that is root 2 over 1, which is root 2. Secant is the reciprocal of cosine, which is also root 2. And finally, cotangent, well, when we take the reciprocal of tangent, we flip 1 over 1 that's still 1 over 1. So the cotangent of 45 is also 1. That is the reciprocal of the tangent of 45 degrees. So there's your 6 values for a 45-degree angle. Okay, let's do it again, but now we're going to do this same idea for a 30-degree angle whenever the computer decides to change the page. Okay, so now what we're going to do is we are going to use our 30, 60, 90 triangle. So we have our 30, 60, 90 triangle. So that's a 30-degree angle. This is a 60-degree angle, which has side lengths of 1, 2, and the square root of 3. For the 30-degree angle, which is the one that we're working with, 1 is going to be our opposite side, root 3 is going to be our adjacent side, and 2 is going to be our hypotenuse. So we will start by running SOHCAHTOA to come up with the sine, cosine, and tangent of 30 degrees. So the sine of 30 degrees is opposite over hypotenuse, or 1/2, 1 over 2. The cosine of 30 degrees is adjacent over hypotenuse, which would be root 3 over 2. And the tangent of 30 degrees would be opposite over adjacent, 1 over the square root of 3. That would require us to rationalize the denominator by multiplying the bottom and the top by the square root of 3, and it would give us root 3 over 3. Then we go and we use our reciprocal identities. So the cosecant of 30 degrees, cosecant is the reciprocal of sine. 2 over 1 is 2. The secant of 30 degrees is the reciprocal of the cosine. 2 over root 3. So we have to rationalize our denominator. This is going to be the ugliest one in the whole set. That would be 2 root 3 over 3. And the cotangent of 30 degrees would be the reciprocal of the tangent, which would be root 3 over 1, or root 3. So there are 6 trig values for a 30-degree angle. One more of these to do, and that is for the 60-degree angle. We're going to use the exact same picture. So we're still using our 30, 60, 90 triangle. Which has side lengths of 1, 2, and the square root of 3. However, now, instead of using the 30-degree angle to name the sides, we're using the 60-degree angle, which means the square root of 3 will be our opposite, 1 will be our adjacent, and 2 will still be our hypotenuse. So we go and we use SOHCAHTOA, just like we did in the previous 2 examples. The sine of 60 degrees is opposite over hypotenuse, root 3 over 2. The cosine of 60 degrees is adjacent over hypotenuse, or 1 over 2, 1/2. The tangent of 60 degrees is opposite over adjacent, which is root 3 over 1, or root 3. Once we have the sine, cosine, and tangent, we use our reciprocals to get the other 3. So the cosecant of 60 degrees is the reciprocal of the sine, which would be 2 over root 3. We would need to rationalize the denominator by multiplying the bottom and the top by the square root of 3, giving us a final answer of 2 root 3 over 3. The secant of 60 degrees would be the reciprocal of the cosine, 2 over 1, which is just 2. And the cotangent of 60 degrees would be the reciprocal of the tangent, 1 over the square root of 3. Pen got away from me a little bit there. Let me clean that up. There we go. Which would require us to rationalize the denominator by multiplying the bottom and the top by the square root of 3, and would give us root 3 over 3. Alright, so we came up with the 6 trig function values for all 3 of our major angles. What we are going to do now is we're going to put all of that information together onto a single slide that will then be used as a reference item for the rest of the course. Now, it's worth noting that this item is also found on page 50 in your textbook. So this reference item is going to list the 30, 45, and 60 degree angles, all 6 of their trig function values. So we did 45 degrees first. If we go back and we look at that slide, the sine of 45 was root 2 over 2. The cosine was root 2 over 2. The tangent was 1. The secant and cosecant were both the square root of 2. And the cotangent was 1. Then we did 30 degrees. The sine was 1/2. The cosine was root 3 over 2. The tangent was root 3 over 3. The secant was 2 root 3 over 3. The cosecant was 2, and the cotangent was the square root of 3. And finally, we finished up with 60 degrees. The cosine was root 3 over 2. The sine was root 3 over 2. The cosine was 1/2. The tangent was root 3. The secant was 2. The cosecant was 2 root 3 over 3. And the cotangent was root 3 over 3. That does it for this video and for section 1 of chapter 2's notes.